Hey, hi everyone. Welcome back to the Topos Institute Colloquium. Today we are pleased and honored to have Christine Tasson from Supero, who will be speaking to us about semantics for reactive probabilistic programming. So Christine, whenever you're ready.
Okay, thank you. Good morning or good afternoon, everyone. I am very happy to present this joint work with Guillaume, Baudart and Louis Mandel. Well, in order to develop critical embedded systems, such as planes, cars, or robots, which interact with stochastic environments, the industry needs domain-specific languages with strong safety properties. So, reactive programming languages, such as SCADE, allow to implement softwares that react safely with their environment. For instance, with deterministic and time-reliable reactions. And probabilistic programming languages, such as Stan or Pyro, implement Bayesian inference. Bayesian inference is a statistical framework that allows to learn probabilistic distribution conditioned on observations. And my colleagues, Guillaume, Baudart and Louis Mandel, have contributed to the development of Probabilistic, which is an academic, reactive, and probabilistic programming language. So the goal today is to study its semantics, and because during compilation, programs are transformed and optimized, I will show you how to use these semantical tools to prove soundness of program transformations. But let us start with a small example as an introduction, a model of a flight. So it's a flight tracker. Imagine you are in a control tower and you have a radar that has to estimate both the speed, which is assumed to be constant, and the position of the plane. It can then communicate this information to the plane, and the plane can control its trajectory, change it so that it follows the planned trajectory. So we assume that the time is discretized, and we want to compute the stream of position at time t, t+1, and so on. Okay, so the system, we assume that to model the evolution of the system, we assume that the plane is at cruising speed and altitude, and the movement is straight, and the radar has to track the plane. And we will use Bayesian inference to evaluate the randomness. There are two sources of randomness. First, the environment, if there is wind or whatever, the environment can randomly influence the position. And there is another source of randomness, which is the measures. The radar measures are noisy, and we want to take this into account during our observations. So what we want to do is to compute the stream of conditional distributions of the speed and of the position given the radar observations. Okay, so the goal today is to study a programming language and to apply semantical tools of probabilistic reactive programming and to prove soundness of program transformations. And in the first part, I will first introduce the semantics of reactive programming. So for this part, we don't have any probability, and we will introduce them after. So in our example, we will model the position of the plane with this variable position at times t+1. So the current position will depend on the previous position, and it will be equal to the previous position plus the speed, which is assumed to be constant. And we assume that we are in a synchronous paradigm, so we will have this stream of position to compute. Okay, so now we have the radar measure observation. We will observe the angle and the delay of the computed from the plane position. So the radar measure can be computed by a function from applied to the position. Okay, and what we want is to evaluate the difference between the ideal radar measure and the observed, which is computed from the position, and the observed radar measure, which is an input of our system. So we can use, to implement and to model this system, we can use block diagrams à la Simulink or Skate, which are languages used in the industry, or we can use a synchronous program à la Lustre or Zelus, which are academic programming languages. So let me detail this code. We have a model of the tracker, which takes as inputs the observation of the radar measure, and which gives as output the current position and the distance between the observed and the computed radar measure. Okay, so at each time step, I take this input and I have to produce these two outputs. How can I compute them? With these mutually recursive equations. At initial step, the position is the initial position, and then the current position would be equal to the previous position plus the speed. The radar measure will be computed as the image of the position through this function, and the difference will be computed from this computed measure and as the difference between this computed measure and this observed radar measure, which is given as an input. Okay, so now that I have this tracker, I can use it and give the current position and the distance between the observed and the computed radar measure to a controller that will produce an action that will be sent to the plane that can change its trajectory to follow the planned trajectory. Here, I'm using the synchronous paradigm. In this paradigm, we have the synchronous hypothesis, which says that all the inputs are arriving simultaneously, and the computation is instantaneous. So that because the time is discretized, at time t, I have all the inputs arriving simultaneously. I compute immediately the output before having at next time all the inputs arriving. So it's an abstraction of the time that allows me to ensure strong safety property, and to give a well-defined semantics to this language. Moreover, the expressivity of the language is restricted to ensure determinism and causality. So we ask the recursive equations to be productive. That means that we ensure that a criteria is satisfied, so that all the fixed points computing the solution of these equations converge. Moreover, we ask for causality. That means that the nth output is computed, depends only on the n first input of the system. If we have all these assumptions that are verified, then we can compute the semantics of the program. So if I have a program E of type A, it's the type of the outputs, given the context, so the type of the inputs, then the semantics of E will be a function from the stream of inputs to the stream of outputs. And because the syntax is restricted, we can ensure all this property under the synchronous hypothesis. Okay, so let's have a look at our example and the function which will be associated. It takes a stream of inputs, the stream of radar observations. And the nth element of the stream of outputs corresponds to the position at time step n and the difference at time n. P0 is the initial position, Pn is computing from the previous position plus the speed, and the difference is the mathematical difference between the computed radar measure and the observed radar measure that comes from the input. It's the input at time n. Okay, so because we are in the Topos colloquium, I have to relate this causality property with the topos of trees that was introduced by Baudart to study guarded languages. And in the topos of tree, we have this discretized time. The natural numbers encodes the time steps. And the presheaves will encode the growing knowledge that we have on the system during time evolution. So for instance, if I look at stream of bool, at time 0, I will have the singleton, no information. Time 1, just a Boolean. Time 2, a list of 2 Boolean, and so on. And this map in the presheaves are the restriction maps that ensure the coherence between list of time n and list of time n-1. That means that following this line, we have an extension of the lists. Okay, so now if I look at the semantics of a program, it's a morphism in the topos of tree that is a natural transformation between, say, the stream of inputs to the stream of outputs. And this naturality ensures the causality property, indeed, because this is commuting, the list of type n will depend only on the nth approximation of the input stream. Okay, so this topos framework is really nice to reason on synchronous and on guarded reactive languages. And you can have a look at this article, which shows how we can generalize synchronous programming using ideas coming from the topos of trees. But here we are interested in probabilistic reactive systems, and I will go back to more concrete semantics. So in synchronous programming, we have also operational semantics. This operational semantics corresponds to the way the programs are compiled and evaluated. And we will use a labeled transition system in which we have states that represent the history of all the variables that are in the programs. We have inputs, which are labeling our transition system. The outputs will be our observables, which are the values. And we have a projection function, which takes the current state, observe the output value produced by E, and we can compute the initial state from the text of the program. And finally, the transition function will take the current state S, read the input, gamma, and produce next step. Let's have a look at our example, so our tracker. What will be the state? We need the current position, the previous position, and the current difference between the computed and the observed radar measure. Okay, so why do we need that? We need that to observe the output, the position, and the difference, but also to compute next state. Indeed, if I read an input, so observed measure from the radar, I can compute the difference between the computed radar measure from the new current position and the observed radar measure. I can compute the current position from the previous one, which was here, and I can memorize the previous position. Okay, so starting from previous position, current position, and this difference, reading the measure, the observed radar measure, I produce next state, previous position is current position from previous state. Current position is the current position of previous state plus the speed, and I can compute the difference between observed and computed radar measure. Okay, so what about the initial state? The initial state is made of the initial position. I have no previous position, and I cannot compute any distance between the computed radar measure and the observed radar measure because I have no input for the moment. So it's better. Okay, so just as a remark, here I have said that the state contains all the history for every variables, but my state here is made only of 3 things. So I use the fact that because my syntax is restricted, the memory will always be bounded, and it will be bounded by a number related to the number of last. Why? First, because I have a finite text describing my program, so I have finitely many variables, and the history that I need to memorize is equal to the number of last that appear, the number of times I need to use the previous positions, the previous values of the variables. Okay, so even if I should put all the history from the beginning, I can only memorize a bounded size of a memory of bounded size, and it's really useful to prove that we won't have any memory overflow with a synchronous program. What is very nice with this synchronous programming is the equivalence between denotational and operational semantics. So for every stream function, going from stream of inputs to stream of outputs, I can relate it to the transition system if I denote run at time n that takes the inputs from the n first inputs, the values that I have observed here. So I start from the initial state, I read 1 input, 2 inputs, 3 inputs, n inputs, and I observe the output value. And I call that the semantics, the run semantics of E. Then, under 2 assumptions, the first one is all recursive equations have a unique solution for every input. And the second one is the program is causal. The output at time n only depends on the history. Then I can relate the stream of outputs with the outputs that are produced by the transition system. The nth element is equal to the value produced by the transition system at time n. Okay, so now we are ready to introduce some probability and Bayesian inference. Okay, so let's go back to our example. We want to take into account the randomness and to model the influence of the environment on the position. So we will assume as a prior that the position at time t plus 1 follows a probability distribution, a Gaussian, which is centered on the ideal position, which is previous position plus the speed. And this Gaussian, we assume that it has some variance. Okay. So this is to model the random influence of the environment. But there is another source of randomness, which is the measures are noisy. And we want to compare the ideal measure, the computed measure computed from the position, with the observed measure. And we can assume that there is a white noise. That means that the observed radar measure follows a Gaussian distribution centered on the ideal radar measure. Okay? And our goal is to compute the stream of posterior distribution, the stream of conditional distribution of the position given the observed radar measures. And to model this system, we will use Probabilistic, which is an academic language, both reactive and probabilist. The reactive part follows the Zelus language, and the probabilistic part follows constructions from Pyro or Stan. Here we have our construction. This sample construction introduces the prior distribution. It says that position follows this Gaussian distribution centered on this computed next position. The conditioning is implemented with this observed function, which says that we will prefer position such that the computed radar measure is close to the observed radar measure. So we replace the difference that we were computing in the completely reactive program with this probability by scoring the sample of positions that induce close radar measures that are observed or computed. Okay, so now I can infer, that is, I can compute the posterior, the conditional distribution with this construction infer and give it to my controller. So because probability distribution are infinite objects and my computer is finite, I have to use algorithm to approximate the probability distribution that is inferred. So I just give you some hints on how it's approximates. What I can compute is the new position from the last position, which is just last position plus the speed. And I have my multivariate Gaussian distribution, and I can sample in this distribution. So the sample construction will construct finite discrete distribution by sampling n position in these Gaussian distributions. I will have more samples which are close to the ideal position because they are more likely to appear, and less samples that are far away with small score in this density. So at the beginning, when I do the sample, I have n samples with score 1. It's a uniformly distributed distribution over this position. Now, when I arrive at this line, I will score all this position with respect to the observed radar measure. So I have got the radar measure, and I can compare it with the ideal radar measure computed from the position. So I will score with this density at the radar observation, and if the radar observation is far away from the position, then the position will be scored with a very small score. If it's close to the radar observation, then it will be scored with a big score. So now the last step in the inference is to renormalize to have a probability distribution because I have changed the score. Okay, so in this way, I have a finite approximation of the posterior distribution that I am interested in. So this is an inference algorithm that allows me to compute and to approximate this program. But today, I am interested in the ideal semantics, so I am not going to study such algorithm from now on, but study the ideal semantics, the measure semantics. Okay, so let's move on to the probabilistic reactive semantics. What I want to compute is a stream of probability measures given the stream of inputs. This will be the semantics of this construction, infer E. But for this, I have to solve recursive equations. Why? Because I want to have a schedule agnostic semantics. Why? First, it's inherited from block diagrams languages that are standard in the industry. And second, when we manually schedule the equations, we get something which is not modular, and we are interested in composition, in modularity, and so on when we program. Okay, so my problem is to compute the fixed points of these equations in the measure semantics. So this is a very simple example to show you where is the problem in computing fixed points in the measure semantics. So I have X, which is sampled in a Gaussian, and I want Y to be equal to X. Okay, so when you read the program, I think that you think that the semantics that we want is a probability distribution following a Gaussian with 2 points which are equal. X and Y have to be equal from these equations. But if I compute the fixed point in the measure semantics, what happens? Sample Gaussian has the semantics of sample Gaussian is the probability distribution, is the Gaussian distribution. So X is equal to the Gaussian distribution. Y is also a probability distribution, which is a Gaussian distribution. Then E is a probability distribution, which is the tensor of two Gaussian. So if I sample into E, I will get two different values from the Gaussian distribution, and not the same value. Okay, so it's a problem which is related with evaluation, call by value, call by name, and so on. But there is another problem. If I look at the measure semantics, the least element is the nil measure. And if I want to apply least fixed point computation, I will stay with the nil measure. So I have to try and find another solution, which is classical. It's come back to Kolmogorov theory of probability, which says, well, the randomness is externalized. We take a universe of probabilistic events which represents randomness, and then we use random variables from this universe to a domain of value which are interesting. So our solution is to externalize the random seeds and to compute the fixed point in the value domain. And this trick was already used in QBS, which is a standard model of probabilistic programming, to solve recursive equations. Okay, so if we want to externalize randomness in order to solve recursive equations, we have to add an assumption, which is always most often are always satisfied in programming languages. We ask that all probability distributions have density with respect either to the counting measure or the Lebesgue measure, so that we can redefine the probability distribution with respect to the random seeds R, which is in 0, 1, and use the inverse cumulative distribution function to recover the values. Okay, so we are allowed now to do this change of variable, and instead of taking the universe of rho, we can change the probabilistic universe and go to 0, 1, which simplifies a lot the computations. So the sampling semantics takes K, the number of samples that appear in the program. Then the semantics will take the stream of inputs and the stream of random seeds that are now considered as an external environment. And with this stream of inputs and the stream of random seeds, we can produce the stream of value, the stream of outputs that are scored by positive reals. Now that I have these two streams, I can compute the stream of measures by integrating over all the streams of random seeds. So it's a really big integrate, which is correct, but it's even easier to compute because we have assumed that our program are causal. That means that the nth element, the nth probability distribution, only depends on the preceding events. So on the n first random seeds. So I have only to integrate on this finite dimensional space. Okay, let's move on to the operational semantics. I use the same trick. The sampling, and I define a sampling labeled transition system. The states now encode the history of all variables and the score. The inputs and the outputs are not changed. The projection will observe the output values from the state and will preserve the score. The allocation is the initial state and score 1, because we don't know anything about the probability at this moment. And the step function will take a state, a score, an input and a random seed, and produce next step and compute next score. So modify the score. I can recover a classical stochastic label transition system in the classical sense. Indeed, I can define a step function which take a state and produce a probability distribution over states just by integrating over the random seed that I got from the random universe at time n. Okay, so let's have a look at the semantics. So now I compute only the position, because the difference between the observed and the computed radar measure are encoded in this likelihood, in the inference. So the states will be made from the previous position and current position. The observation will be the current position. The initial state is the initial position, and the first score is 1. Now, if I know the state and the current score, I read an input value and a random seed, and I will produce next state. Next position is computed from the random seed by inversing the cumulative density function from the Gaussian to get back the value sampled in the Gaussian with this random seed. So now next position is p prime plus the speed, and next score is previous score multiplied by the density function centered in the computed radar measure, and this density function is computed at the observed radar measure. Okay, so that I will score with something which is measuring the likelihood of this position. Again, I have a strong relation between the denotational semantics, which produce stream of outputs and stream of scores, and the operational semantics, which is a sampling label transition system. Again, I can prove that the sampling semantics at time n will be equal to the value and score that are produced by the transition system. And because the stochastic or the probability measures that I want to compute are related to this sampling semantics, and they are equal, I got the strong equivalence between denotational and operational semantics over probability measures. Again, under the condition that recursive equations have a unique solution and the program is causal. Okay, just a remark here to get back the measure semantics. For this denotational semantics, I have to integrate over streams of random seeds, and here I have to integrate over finitely many random seeds. Okay, so now that I have defined this semantics, I can use it to prove program equivalence. So the first thing is to define the observational equivalence between probabilistic programs, reactive probabilistic programs. And we say that two programs are observationally equivalent if for all input stream of inputs, they will produce the same stream of probability distributions. This is a very simple example of equations that we want to prove. This is a part of the equational theory of our language. This says that if I sample in distribution E1 and add with a sample in distribution E2, it's the same thing as solving recursively these equations. So X is sampled in E2 and Y is sampled in E1. And then afterwards, I do the addition. So it's a very simple equation, and everybody can see that it's observationally equivalent. But if you look at complicated program transformation, they are all made from these little rewritings that are simple to prove. So it's really important to prove that kind of equality. Why it's difficult, why it's not immediate to prove that they are observationally equivalent, if we look at the states associated with the transition system, they are completely different. Here I have no states, I have states coming from these equations. So I have to manipulate the transition system to make them, to relate them. And I have to use stochastic dissimulation. I will say that the two stochastic transition systems that are associated to E1 and E2 are stochastically dissimilar if there is a dissimulation. It is a relation between states, such that for all inputs and for all states, S1 and S2, which are related, if I do a step in my transition system reading gamma and produce a probability distribution over states, then there is a probability distribution over states of my second system, which will be produced by reading gamma starting from S2 in my second system. And I have a stochastic dissimulation if there is a coupling that is a probability distribution over pairs of states, such that the marginal of C on the first component is phi 1, and the marginal on the second component is phi 2. And I asked, moreover, that the support of the coupling, which is a relation C prime included in my bisimulation, so this condition is that C prime is the support of my coupling. So the support, if I take two states in the support of the coupling, then the observations are the same. Okay, so the coupling is a probability distribution over states on which I do the same observations, so that because of adequacy, I can prove that they will produce the same observation. They are observationally equivalent. So to have a bisimulation, I need to have this condition. If S1 reduces to phi 1 by reading gamma, then there is a blah blah on S2, and vice versa. If S2 reduces to phi 2 reading gamma, I have the same condition on S1. Okay. So this is quite standard, but it's difficult to use to prove observational equivalence. And the proofs are a little bit counterintuitive. We can do them, but it's a little bit hard to reason on that. Okay, so we introduced a denotational tools to prove this observational equivalence. And it is based on sampling bisimulation. So we go back to our sampling semantics, and we want to relate the sampling semantics of E1 and E2. And to do that, we need to do something on the random seeds, because on the left-hand side, I have two random seeds, two streams of random seed, one for E1, one for E2. But on the right-hand side, I have first the one for E2 and then the one for E1, and I cannot mix them. If I want to relate the observation, I need to do some transformation over the random seeds. And we could have something even worse. Imagine I have a third equation here. X is equal to sample E2, Y to sample E1, and Z is equal to sample E3. But Z is not used in the output. So I have used a sample, and I have used a random seed, and I do not use the output, the sample, in my final result. So here on the left-hand side, I have two random stream of random seeds, and here on the right-hand side, I have three streams of random seeds. So I really need to do something to relate them. So if I have a stream of random seeds here, I will project them. If here I just have a permutation. So it's always simple transformations that can be encoded with a function. So E1 and E2 are sampling bisimilar if there is a function psi from the random seeds of E1 to the random seeds of E2, such that this function is preserving uniform distribution. That means that the push forward along psi of the Lebesgue measure over K1 random seeds is equal to the Lebesgue measure over K2 random seeds. So I'm really relating the randomness for E1 and for E2. The second condition is that the computed value and score, stream of value and score by E1 and by E2, when E1 is fitted with the random seed R and E2 is fitted with the random seed psi R, psi applied to a stream of random seeds, it's just the stream of psi applied to the random seed. Okay, so it's just a lifting of psi. So if the value and score computed with R by E1 and with psi R by E2 are the same, then I've got my sampling bisimulation. And I can prove that the sampling bisimulation induce the observational equivalence. How I prove that? I just apply a change of variable formula along psi. Okay, so let us note SI, the stream of values, and WI, the stream of scores produced by EI. Then the stream of probability distribution is computed by this integral. I can change R by psi of R here and here. It is because the score and the value are the same. And then make a change of variable, R prime is equal to psi of R, to get my stream of probability distribution for the second system. And so the streams are the same. Okay, it's not that easy to reason on the stream of probability distribution. And we generalized an inference system inspired from this article that certify a compiler for Lust. So we generalized it to the sampling semantics. It is for the deterministic, not probabilistic reactive semantics. So we have sequence which says that E produces the stream of values and stream of score given the stream of inputs and stream of random seeds. We have several rules that I won't describe here, but the idea is to represent as an inference system our proof that two programs produce the random seeds. We can do that because this system is sound. That means that a sequence has a proof if and only if the stream of values and stream of scores are the semantics of the program. Okay, so I can use this inference system to prove now that these two programs are observationally equivalent. I just need to prove that they have the same sampling semantics. And here, I use my inference system. I have these two hypotheses. And if I use my inference system on the second program, I have a more complex proof, but I have the same hypothesis here, but with a permutation of the random seeds. Okay, so I can define psi, which associates R1, R2 to R2, R1, which are the random seeds of each of the systems. And I can prove that I have these hypotheses that are true if and only if these hypotheses are true, because E1 and E2 here do not use X and Y, which are defined in GA. Okay, so this is very simple proofs compared to the bisimilarity of stochastic bisimilarity of transition systems. I also want to mention an application that I am very proud of, which is the proof of a program equivalence that is needed for an inference, which is called the assumed parameter filter. So the assumed parameter filter algorithm, inference algorithm, is used to infer constant parameter and state parameter in temporal models. And I can explain it on our example. So now I want to infer two things. The distribution over the speed, and we assume that the speed is constant over the time. And I want also to infer the distribution over the position, and the position is evolving during along the time. Okay, so I add this part in my program, which says that theta is my distribution over the speed is following a Gaussian distribution. Okay, so sequential Monte Carlo inference, which is used in Probabilistic to infer probability distribution, is not a good algorithm to approximate constant parameters, because at each time I will sample in the same distribution and I will duplicate particles. I will duplicate the particles that have the biggest score. So at the end, I will have what we call an impoverishment, which means that I have only few particles from the beginning. So it's not at all representing a good approximation of the constant distribution. So for constant parameters, it's better to use symbolic inference. So we have two different algorithms for constant parameter and state parameters. So this algorithm necessitates to first transform the program so that we can extract the constant parameters and reason differently on them. Because if they are hidden inside the text of the program, I cannot do anything. So here is the text that we get after the transformation, sorry. And the definition of the inference on this text of the program is the usual inference, but where we have externalized the constant parameter. And we can prove the soundness of this transformation by using our sampling bisimilar semantics. Each step of our transformation is proved by exhibiting a function between the random seeds of the first and the second part of the transformation. So we have two proofs for this soundness result. The first proof is a sampling bisimulation, which is using stream functions and this change of variables. And the second one is by stochastic bisimulation. There we are using states and stochastic Laval transition systems. But it was what we experience is something which was already remarked by Kahn in, I think, 74, which is that it's really counterintuitive to reason on states because the states do not use or reflect the structure of the program. So it's really more easy to think about the function interpretation, the stream, about the streams. Okay, so you can find the material of this talk in this preprint, which is available on the archive. And to wrap up, I have introduced equivalence semantics for probabilistic reactive program, both operational semantics and denotational semantics. I have shown you tools to characterize observational equivalence, either with stochastic bisimulation or sampling bisimulation. And I have shown you how we can use them to prove basic equations and to prove more involved transformations of programs. In the future, what we want to study is to understand more closely how we solve recursive equations in probabilistic programming, and also to use probabilistic distance to finalize the proof of soundness of the APF inference algorithm, because what we proved today is just the first step. It's the proof that the transformation of the program is correct, not the inference algorithm. Okay, thank you very much.
Thank you so much, Christine. So we're going to go into the question time for our colloquium. And here, there are two ways to ask questions in our colloquium. The first is you could ask the question, you could raise your hand and I'll call on you to unmute yourself. Or if you're not able to unmute yourself for some reason, you could type your question in the chat and I'll be happy to ask on your behalf. So yeah. Feel free to raise your hand if you have a question or type them in the chat. So I see that we have Kevin. Kevin, you have a question.
Hi, thanks very much. Interesting talk, Christine. I'm wondering, this is a little bit probably off the target of your work, but I wanted to ask a little bit about applications. Do you hope that a language like this, being a synchronous language, could actually be used in real time, say in doing some, well, you had the radar example, so in doing some aerospace?
Well, in aerospace, you know, we use really simple version of probabilistic programming, which is I forgot the name just for now, but so the tool that we use to infer probabilistic parameters are special case of this kind of program. So the answer is yes, of course we can use it, but we won't use all the expressivity of the program first, and I'm not sure we can use them for online inference.
Right, that was kind of the question. So it may be the computational heaviness of some of this inference is still a bit much to expect to do in real time online.
Yeah, synchronous programming languages are really useful for critical systems, and that's why we are allowed to restrict the expressiveness of the language, because we want to ensure this safety. If we add some Bayesian inference, we move to another word where we use approximation of probability distribution. So we change of word. So I'm not sure about the answer.
Sure. Thank you.
Thank you, Kevin and Christine. So Valeria, I see you have a question.
Hi, Christine. Yeah, it was very interesting, but I don't know much about any of this stuff, so I have a generic question. I know that dealing with probabilities using category theory is not a closed book. It's not, there's no unique way of doing it, and people have lots of different positions on that, right? And I kind of wondered whether, in particular, your notion of stochastic bisimulation, how canonical this notion is, and whether you could kind of point me into some sort of direction of where is the choice, the space of choices that you could make in this kind of program, right? Because I mean, of course, I do know that we kind of normally want to have operational semantics proved equivalent to the denotational semantics. But in this case, the denotational semantics, there's lots of them. And I presume that the operational semantics, there's lots of them too, right? So I kind of wondered how canonical the notions that you're discussing are, if you have any links on that.
Okay, so first of all, so there are many different approaches to denotational semantics for probabilistic programming languages, but they're all related. I mean, mainly there are three approaches. Either you say that the probability, the randomness is externalized, and you take a schedule of random seeds, as I showed at the end of the talk. Either you consider the probabilistic mergers, either so the kernel semantics. No, actually you have only these two semantics, which were already in Cousin work on the semantics of programming languages. Then the extensions that I know are for higher order, and there are many different semantics, but they are different in their formalization. The idea is always the same. You use some measure tests or for stable counts, or you use some pre-shift for QBS. But the idea is to have this randomness externalized, and to have the random variables to interpret the sampling.
Right.
So they are really related when you look into the details. It's just the formalization or the presentation which is different. So that's the first thing. And considering the operational semantics, the stochastic bisimulation that I presented is the standard one. And I just reformulated the synchronous programming, synchronous paradigm in this way. Because if you have a look at our paper on the synchronous programming, they present the operational semantics through a co-iterative semantics, which is a little bit different, but it's just writing details.
Right. So, I mean,
okay.
if
you want, yeah.
No, I was just kind of thinking that, I mean, I thought there were lots of different operational versions as well, and that people would kind of normally kind of talk about weak bisimulation of this shape or strong bisimulation of that other shape, you know, that there was a zoo of these relations. And so that's why I was asking how standard, but you're saying that it is the standard one, this notion of stochastic bisimulation.
I think so, but I may I may be wrong. Actually, it's a generalization of
No, you know, if nothing else comes to mind, if there's no kind of specific alternative,
well,
then I'm good.
yeah. I can point you to some survey on stochastic simulation if you want to know more.
Mm-hmm. And can I ask one more kind of quick question on that? I mean, before you started talking about the probabilities, you talked about this Guato paper, a generalized modality for recursion in Leaks 2018. And
Yeah.
I was wondering, what is the modality doing there? What is this modality that's for recursion? I mean, is it modality in the sense of modal logic, the stuff that I know?
Here in the
Yeah, I don't remember exactly which, but it was
here. The
yes.
modality for recursion. So this modality is speaking of time warps. In the synchronous programming, you have all the inputs that arrive at the same time so that you can compute the outputs. But in real time, in real reactive programs, you may have one input that is arriving at each time and one input that is arriving at first time and then third, fifth, and so on. They don't have to, in a real system, they don't have to be synchronized. So how do you deal with this time which is which is not synchronized in practice? And it's a way to use the topos of trees to change the modality, the desynchronization to allow one of the inputs to last longer.
Right.
Okay, so it's warping times, making time vary modality.
I see. Okay.
So it's not related really to a modal modal logic for time or something like that.
Mm-hmm. Okay, thank you. Thank you very much. I mean, thanks also for the generic explanation of the different ways of dealing with probability. It's always helpful.
You're welcome.
Thanks, Valeria. Thanks, Christine. Any more questions from the chat? If not, I have a question. So, I'm wondering if your methods here could be used for proving the kinds of statements that people make in temporal logic, such as like some event will eventually happen or some event will always happen. It's because there's stochasticity here, and I imagine that want to prove that certain things will happen with high probability or with probability one will eventually happen. Is it kind of very different approaches from the kind of techniques you've developed here?
I'm not sure about the relation between the two of them. I cannot see at this moment how we could use this kind of approach to prove some temporal logic, like it will eventually happen with almost surely or thing like that. I don't know. I have to think before answering such a question.
Okay, sorry, it's
Thank
kind
you
of out there. Yeah, thanks, Christine. Okay, we are gonna end the YouTube live stream now, and let us thank Christine again for really intriguing talk. Thank you so much.
You're welcome. Thank you for the invitation.
Okay,